Hello and welcome to this free preview lecture series of my on-demand FE Electrical and Computer Exam Preparation course. In this lecture, we are going to discuss three-phase circuits, which form the basis of power system, network power system analysis. And even after clearing the FE Electrical and Computer Exam, you're actually going to encounter them again in the PE Power exam preparation because they're so fundamental to power system analysis. So getting a good understanding of three-phase systems is going to set you up for success not only in the FE exam, but also in the PE Power exam. Before we dive into the content, I would really appreciate if you could like this video and click the bell icon and the subscribe button if you haven't already done so. Hello and welcome to this lecture on the topic of three-phase circuits, which is a subsection of power systems. Learning objectives of this lecture include understanding three-phase circuits. We will start off the lecture with an introduction to three-phase circuits. We will discuss the benefits of three-phase circuits and why they are so important in power systems engineering. We will look at two configurations, the Y network and the delta network. Then we will discuss transformation between delta and Y network, and at the end we will look at three-phase power. To put it simply, three-phase circuits refer to a system of generation, transmission, and distribution of electricity in which at least three conductors are involved. Virtually almost all electricity is generated and distributed as three-phase power rather than single phase. And a balanced three-phase system is the one in which the current and voltage of each phase is 120 degrees apart and there is equal loading on each phase. So the diagram on the right shows phase 1, phase 2, and phase 3. You see that they are 120 degrees apart and the amplitude of each of these phases is identical. So obviously there should be some inherent benefits of using three-phase systems, which explains why we prefer them over single-phase systems for generation, transmission, and distribution of electricity. So in terms of the benefits of three-phase system, the first benefit is that although you increase, so when you increase the number of conductors from 2-wire to 3-wire, your power transmission actually doubles. So you're going 2x over here in terms of power, and you're only increasing from 2 to 3, it's a 1.5x increase. Okay, so dollar value benefits. Constant torque reduces vibration, so you always have some voltage appearing. Okay, so there's the first peak, but in between the peaks you can see that there's some voltage appearing as well, so that reduces the vibration. Three-phase machines use less material for same power rating, so again economic reason. And three-phase machines start more easily than single-phase machines, so you can say reliability / simplification of design, all of which actually translates into dollar. And the cost of three-phase system is less than single-phase system. We end up using fewer amount of conductors, and there are lower losses in a three-phase systems. So that's why virtually everywhere, as I mentioned, generation, transmission, and distribution of electric power is done in three-phase circuits as opposed to single-phase circuits. So within the three-phase systems, we have two types of arrangements. The first one is a Y network, and the second one is delta network. We will explore each one of them in detail. And in terms of transmission and distribution voltages, I believe you would know that high voltages are generally reserved for transmission, especially for longer distances. So we are talking about 115 kV, 230 kV, and 500 kV and above. There's also high voltage DC transmission, but that's not really an AC system, but that can go upwards of 800 kV and extra high voltages of 1000 kV plus. So there are some systems which interconnect continents or big countries or huge distances. You may even see voltages upwards of 1000 kV. And then for distribution, this is typically done at low voltage and medium voltage depending on at what point in the power system you are. So 15 kV is pretty standard, 5 kV is pretty standard, and residential voltage distribution is typically done at 480 volt and 600 volts. Y network. So Y arrangement is one of the two arrangements for three-phase circuits, and in the Y arrangement, the three-phase Y source is configured such that it has three voltage sources that are connected to a neutral. So it literally looks like Y, like the letter Y. Okay, and here's example. So you have phase, if I can call this as A, B, and C. Phases A, B, and C are arranged such that they share a common point, which is the neutral. And then between each phases, so between B and C, you have line voltage BC, VBC. Between A and B, you have line voltage A and B. And between A and C, you have A and C. And loads can also be connected in Y network using 3 or 4 wires. When we use 3 wires, we basically don't bring out the neutral. But if you end up using 4 wires, then you basically bring out the neutral. So that becomes a 4-wire system, and that allows you to feed single phase loads as well. So depending on where exactly you are in the power system network, you may or may not want to bring out the neutral, and also depends what type of grounding you are doing. Okay, if you're doing resistance grounding, then neutral is typically not brought out. If you have a solidly grounded system at low voltage, for low voltage applications, typically neutral is brought out. But more and more, the preference, it seems, is that neutral is derived as close to the loads as possible. So you might introduce, for example, if you have MCC feeding a bunch of motors and then you have utility panels, then sometimes the MCC would still stay as a 3-wire system, but downstream of the MCC you will introduce a dry type distribution transformer, and you will derive a neutral from the distribution transformer, which will be feeding a distribution panel, a lighting panel, and so on and so forth. So rather than bringing in 4 wires from the service, you basically generate neutral close to the load. Let us now take a look at mathematical equations for Y network. First and foremost is your voltage. Remember that line voltage is always greater than the phase voltage in Y network by a factor of square root 3, which is 1.732 approximately. Okay, and line current is the same as the phase current. So these are two distinguishing factors of features of Y network, that your line current is equal to phase current and your line voltage is equal to square root 3 times the phase voltage. Okay, so in terms of line current, it's very easy to see, because the phase current that is leaving the phase actually ends up being the line current. Okay, so it's no rocket science over here. Your line current is equal to phase current. Whereas in the case of line voltage, we are basically, so we call this as phase A, phase B, and phase C. So line voltage is VBC in this case, for example, right? So you're measuring voltage between phase B and phase C. So in this case, this voltage is greater than the voltage between phase B and the neutral. So if I were to bring out the neutral, and if I was to measure the voltage between B and N, then that would be less than VBC. Okay. Another feature of Y network is that your line voltage actually leads the phase voltage by 30 degrees. So a lot of students just try and remember the magnitude relationships. Okay, that line voltage is greater than phase voltage by 1.732, and line current is the same as phase current, and they think that's it. Remember that when we are dealing with 3-phase networks, that your phase currents, your phase angles are equally important. Okay, because if you ignore this, if you ignore the fact that the line voltage leads the phase voltage by 30 degree, and you try and solve a question, depending on how easy or difficult the question is or what level of detail the question is asking, then just by skipping this step or overlooking this detail, you will actually get a wrong answer. And chances are that wrong answer will be one of the options that is presented. So don't overlook this. Now in terms of vector, now that we understand the phase current is equal to line current and line voltage is greater than phase voltage by 1.732, in terms of vector, okay, this diagram over here, so you have your phase A along the x-axis as your baseline, okay, at angle 0. So between, and E represents the voltage, so you can see that you have between voltages A and C, you have 120 degrees. Between C and B, you have 120 degrees. And between B and A, you have 120 degrees, right? So 120 degrees apart. Okay. Now, you can notice that EAB, which is the phase voltage between A and B, actually leads voltage phase voltage AN, okay, by 30 degrees. See, so over here we are leading the phase voltage. Again, the phase voltage leads the line voltage leads the phase voltage by 30 degrees. So AB is your phase voltage between A and B, and it is leading so the A and B is the line voltage between A and B, and it is leading the phase voltage VAN, which is between A and neutral, by 30 degrees. Another observation is that this arrow, all of these blue arrows which represent the line voltages, are greater in length as compared to your phase voltages, and they are exactly 1.732 times larger than the phase voltages. Okay, so your line voltage is greater than your phase voltage, or line to line voltage is greater than line to neutral voltage, is the same thing, and your line current is the same as the phase current, and your line voltages lead the phase voltages by 30 degrees. Now there's mathematical derivation for all of these, okay, mathematical derivation explaining the line voltage is equal to 1.732 times the phase voltage, and line current is equal to phase current. I'll try and include some links at the end of the lecture if you want to go through that derivation, or maybe add some notes there, and it will also show that the line voltage leads the phase voltage by 30 degrees. Here's a practice problem for you. We have a balanced three-phase Y-connected load with a phase impedance of this, and it is connected to a positive sequence balanced three-phase Y-connected source with line to neutral voltage of 120 volts with a 30-degree phase. So we are being asked to calculate the phase current. Don't worry about the positive sequence over here, because that is the general nature of the system when it is balanced and operating fine. And it is a concept that we discuss in quite a bit of detail in the PE power exam preparation course. But other than that, what you have to focus on is the impedance that's provided to you, the fact that your load is Y connected and the source is also Y connected, and you are given the phase voltage and you are being asked to calculate the phase current. In a balanced three-phase Y network, phase current can be simply calculated as IAN is equal to VAN divided by Z phase. Okay, so if I were to draw this out, and I always recommend for three-phase systems at least to draw out the network, because it makes things a lot easier to understand and to follow. Okay, so you have, this is pretty simple because you have a Y source and it is a Y load. Okay, and in terms of the Y source, you actually have VAN that is provided to you, and you are being asked to calculate IAN, which is equal to unknown. Okay, and your Z phase is identical for all of these, and Z phase is actually provided as well. So the beauty of Y network, and a lot of times the Y network is much more easier to solve as compared to delta network. That's why we will also discuss Y delta transformation. But in Y network, if you have a Y connected source and Y connected load, then it simply becomes Ohm's law, because your VAN is equal to IAN times Z phase. So your IAN becomes VAN divided by Z phase. So your VAN was given as 120 volts with a phase angle of 30 degrees. Your Z phase is equal to 20 plus 5 j ohm, which is 20.6, and phase angle of 14 degrees. And IAN is simply VAN divided by Z phase, which ends up being 5.28 and 16 degrees. So even in this type of problem, students can make a mistake. As I mentioned before, they tend to ignore, for whatever reason, they tend to ignore the phase angles. And sometimes, because even in the vector diagram that we saw before, you notice that your EAN, which was VAN, was along the x-axis, and the angle is basically 0, right? They believe that the 30 degree only applies to the phase voltages, but then this can shift as well, right? Your phase angle, if that becomes 30 degrees, because it will rotate, so when that becomes 30 degrees, you still have an additional 30 degree phase shift between your line voltages, right? Line voltage and your phase voltages. So just make sure that you give due attention to these phase angles, because in some of the problems they are the deal breaker, because as I mentioned, you may end up seeing two answers and the only difference between the two answers would be the phase angle. Delta network. A three-phase delta source configuration has three voltage sources connected in series with each other to form a closed circuit. Okay, so that actually takes the shape of a triangle or a delta. Okay, and in this case, for example, you can see that if you can call this as A, B, and C, then both ends of the source are connected to the other two sources. Okay, C, you can observe that you have one end connected to A and one end connected to B. For B, you have one end connected to A and one end connected to C. And for A, you have one end connected to B and the other end connected to C. And loads can also be connected in a delta network using 3 wires only, as there is no neutral. So a standard delta configuration will have no neutral. You can add a neutral to a delta network. It's typically done for grounding purposes by making a connection to any of the ends with the ground. So that would be a grounded delta network. But a standard delta network does not have a physical ground, as opposed to a Y network where you basically can take the neutral and ground it through a resistance, or solidly ground it, or even leave it floating. So in the case of a delta network, the neutral is not available right away. So this is your delta network. Again, it's the difference is in the connection as opposed to Y, and it's on not only just connection, it's not only just visual arrangement. We will see that delta network has some distinct features when compared to Y network because of these different connections. Let us now take a look at mathematical equations for the delta network. The first thing that is very obvious is that your line voltage in a delta network is equal to your phase voltage. V line is equal to phase voltage, because you can see here in this diagram that your phase voltage is appearing across the same two nodes, basically where your line voltage is appearing, right? So these points are the same, whether you take them across the phase or whether you take them across the lines. Okay, you connect it across the phase or the line. So if a voltmeter is connected across the phase, that will be the same as connecting it across a line, and it will give you the same reading. So your phase voltage is equal to your line voltage. The difference is in the current. Okay, in the case of a delta network, your line current that is flowing out of the phases here, right? This line current is equal to square root 3 times the phase current. Now phase current is the current that only flows through the phase, through each of these phases. But when it becomes a line current, you can see that it sums up with the other phase, right? And then there are phase angles that you have to take into consideration. That's why it's not 2 times the phase current, right? Because of the 120 degree phase shifts, it is equal to 1.73 times the phase current. Now, if you remember in the Y network, you had the voltage across the two phases being square root 3. The line to line voltage was square root 3 times the phase, and that's because we were measuring across two phases. In this case, your line current is square root 3 times I phase. Now, for some reason, students tend to remember the fact that the line voltage leads the phase voltage by 30 degrees, but somehow they tend to forget an equally important phase angle relationship between the line current and the phase current, which is that your line current lags the phase current by 30 degrees in a delta network. Okay, and we can see that visually by looking at the vector diagram. So in the vector diagram, you have IBA, which is your phase current between phases B and A. Okay, so if I can call this A and B and C, so your IBA is basically this current. Okay, and it lags the line current by 30 degrees. So this is phase A line current, IAA, and it lags the line current by 30 degrees. And you can see that the line current, arrow for the line current in the blue turquoise color, is actually greater than the phase current in length. And this difference is 1.73 times, 1.732 times. Okay, so it can be confusing to remember the delta and delta network equations and Y network equations, but when you draw it out, it will make perfect sense. Okay, because you can see that the line voltage is equal to the phase voltage, and the line current is being summed up as sum of two phase currents. So the relationship is square root 3 times the phase current, and the line current lags the phase current by 30 degrees. This is not so obvious, but once you do the derivation, it will be clear. So these are the key equations governing the delta network. And you can see that by just simply connecting the phases in a different way, we are able to actually come up with altogether different relationships between voltages and currents. As I mentioned earlier in the lecture, generally speaking, Y networks are much easier to solve as compared to delta networks. There are exceptions. So if you have a delta connected delta connected load, and you want to convert that impedance into a Y impedance, then all you have to do is to divide the delta impedance. So this is phase per phase. So you divide the Z delta per phase by 3, and that becomes your Y impedance. So you have the delta impedance, okay, in each of these phases, assuming that it's balanced. Then what you'll do is that to transform it into a Y impedance, this will be 1/3 of the delta. Okay, each phase will be 1/3 of the delta impedance. It's as simple as that. And when it comes to source transformation, if you have a delta connected source and you want to transform it into a Y connected source, it's pretty simple, because if you remember, your phase voltage and the line voltage in delta are identical. So if you want to establish what the phase voltage of the Y network is, you will simply divide the phase voltage or the line voltage of the delta. So in delta, line and phases are the same, divided by square root 3. Okay, and for phase angle adjustment, you will have to make sure that you introduce this factor of square root 3, because the phase voltage in delta lags the line voltage by square root 3, and then you can transform the source from a delta source to a Y source. Here is a practice problem for you on the topic of delta Y transformation. We are being asked to calculate the line current IA, which is provided by a balanced three-phase Y connected source. Okay, so the source is Y connected and the phase voltage is this, and it is feeding a delta connected load. Okay, so this is where it becomes interesting, because you have a Y connected source and a delta connected load. So they've also provided you, I'm also providing you the Z phase, which is 10 plus 2J ohms, and the entire system is balanced, and given these details you have to find the line current. So for three-phase systems, as I mentioned, I always like to draw out the network. So this is how the network looks like at the moment. Okay, this is how the network looks like. I know it's a pretty rough sketch, but your source is Y and your load is delta. Okay, and we are provided VAN and we are provided Z delta per phase. Okay, and we have to calculate this current IAN. Now you cannot simply apply Ohm's law on this, because for Ohm's law you have to have a Y connected source and a Y connected load. So the obvious thing is that we are going to do a source transformation. You are given a Z delta. So we know that Z delta is equal to 3 times ZY, or ZY is equal to Z delta divided by 3. And when you do that, you find that your ZY per phase is equal to 3.4 with a phase angle of 11.3. Now your diagram looks like this. Okay, pretty neat and clean. And you have a source which is Y and a load which is Y. Now you can make use of this ZY per phase and VAN to calculate IAN using Ohm's law. So the final step is to simply make use of the Ohm's law, because we have a Y connected source and a Y connected load. Your IAN is equal to VAN divided by ZY. So IAN ends up being 35.3 with a phase angle of minus 11.3 degrees. And this is amps. Okay, so without doing this source transformation, the problem would have been much more difficult. We would have had to go through more complicated mathematical equations and make use of the phase angles and whatnot. So it's easiest, as I mentioned, to transform the load and the source into a Y network, because then you can simply make use of the Ohm's law. And there's a condition here as well, that your system has to be balanced, and that's what the assumption is. So in the problem statement they tell you that the system is balanced, right? And that's why you can apply Ohm's law. Let us now take a look at another very important concept in three-phase circuits, which is three-phase power. In the earlier lecture we've already looked at single-phase circuits, and we will start our discussion with real power. So as I mentioned, real power is actually indicated by P, reactive power by Q, and apparent power by S. So single phase real power is equal to V phase times I phase times cosine theta. Okay, and we also looked at it in terms of Vmax and IRMS and VRMS in the earlier lecture. So this can also be expressed as I square times R, or V square divided by R. In terms of three-phase power, we have P three-phase, which is simply equal to 3 times P single-phase. Okay, so P single-phase, you would have 3 times V phase times I phase. So as you can see over here, single-phase power is equal to V phase times I phase times cosine theta. So you can simply multiply 3 times V phase I phase cosine theta. That's expressed in the form of phase quantities. Now alternatively, you can now also express it as line in terms of line quantities. and that will translate into square root 3 times v line times I line times cosine theta. So all of these formulas are provided in NCEES FE reference handbook, and they are applicable for both delta and Y networks. Reactive power is almost identical. The only difference is that we are dealing with reactive impedance, and we have sine theta. Okay, so single phase reactive power is equal to V phase times I phase times sine theta. Okay, and we can make use of I square x and V square divided by x for calculation of reactive power as well. And same thing for three phase reactive power. It is 3 times single phase reactive power, which is 3 times V phase I phase times sine theta. And in terms of line voltages and line current, it becomes square root 3 times V line to line I line sine theta. And this is applicable to both delta as well as your Y networks. And last but not the least is apparent power, and this is where a lot of students make mistake. Okay, they think that there's only one type of power, which is real power, but actually what they end up calculating is apparent power. They somehow in the calculation of real power, they somehow miss the power factor, and they think that, okay, single phase power, just multiply voltage with current. What you end up getting is apparent power, and if you're lucky, if the power factor is 1, then you wouldn't even know the difference, right? But if the power factor is anything other than 1, then your answer will be incorrect. Okay, so just keep in mind, when you're simply multiplying a voltage by current, you are actually calculating apparent power. Okay, apparent power includes both the real power and the reactive power. Okay, so three phase apparent power is simply 3 times single phase apparent power, and that can be expressed as square root 3 times V line to line times I line. And power factor is simply the ratio of your real power to apparent power. If you're dealing with single phase systems, that becomes P single phase divided by S single phase. If you're dealing with three phase systems, it becomes P three phase divided by S three phase. And that is your cosine of theta. And if you were to calculate the magnitude, so S square is equal to P square plus Q square. And S is equal to P plus P square plus Q square, square root of P square plus Q square. In this lecture, we introduced three-phase circuits and took a closer look at the Y network, the delta network, and the delta Y transformation. And at the end of the lecture, we also reviewed three-phase power. There's a lot of math involved in three-phase circuits, especially while going back and forth between line and phase quantities. You have to keep track of the magnitude, you have to keep track of the phase angles, and similarly while going between delta and Y networks. And this is where most of the students get confused. So if you are able to develop a deep understanding of three-phase networks, as I mentioned in the beginning, it will not only serve you well for the FE Electrical and Computer exam, but it will also pay dividends because it is a very heavy component on the PE Power exam as well. If you found this preview lecture helpful, I am confident that you will also greatly benefit from the full course that contains over 150 lectures and covers all the topics that are found in the latest NCEES FE Electrical and Computer exam specification. You will also get access to tons of quizzes and mini exams in this course that will help you get additional practice, along with a bonus full-length computer simulated practice exam. This streamlined and well-reviewed course comes with an amazing 30-day full refund policy, no questions asked. On top of all this, I have also included a special discount link in the text section of this video.